Good afternoon, everyone. We are the fourth reporter, and we're going to tackle about Lee Chatelier's principle and gaseous equilibrium calculations.
Lee Chatelier's principle. Lee Chatelier's principle states that if a stress, for example, change in concentration, temperature, pressure, is applied to a system at chemical equilibrium, the system will shift its equilibrium position to counteract the stress and re-establish equilibrium. The behavior for specified changes. First is change in concentration of reactants or products. Increase in reactant concentration. The system shifts forward to consume the excess reactants, producing more products until equilibrium is restored. Increase in product concentration. The system shifts in reverse to consume the excess products, producing more reactants until equilibrium is restored. Next is decrease in reactant concentration. The system shifts reverse to replenish the depleted reactants. Decrease in product concentration. The system shifts forward to replenish the depleted products. Number 2. Change in temperature. Temperature effects depend on whether the reaction is endothermic. Delta H is greater than 0, absorbs heat, or exothermic. Delta H is less than 0, releases heat. Treat heat as a reactant for endothermic reactions and the product for exothermic reactions. Temperature increase. Endothermic. System shifts forward to consume excess heat. Exothermic. System shifts reverse to consume excess heat. So in temperature decrease. Endothermic. System shifts reverse to produce heat. In exothermic, system shifts forward to produce heat.
Equilibrium calculations for gaseous reactions. We use equilibrium constants Kc based on molar concentrations or Kp based on partial pressures for gaseous reactions. Below are example calculations. Example number 1. Calculating Kc and predicting reaction direction. Reaction: N2 gas plus 3H2 gas reversible to 2NH3 gas. At a certain temperature, a 2.0 liter reaction vessel contains 0.20 mol N2, 0.30 mol H2, and 0.10 mol NH3 at equilibrium. Step 1. Calculate equilibrium concentrations. N2 equals 0.20 mol over 2.0 liter is equal to 0.10 m. H2 is equal to 0.30 mol over 2.0 liter is equal to 0.15 m. And NH3 is equal to 0.10 mol over 2.0 liter is equal to 0.050 m. Step 2. Calculate Kc. The formula is Kc over NH3 to the power of 2 over N2 times H2 to the power of 3 equals to 0.050 to the power of 2 over 0.10 times 0.15 to the power of 3 is equal to 0.0025 over 0.0003375 or 7.41. Step 3. Predict reaction direction for new initial conditions. If initial concentrations are N2 equals 0.15 m, H2 equals 0.20 m, and NH3 equals 0.05 m, calculate the reaction quotient Q. Q equals 0.05 to the power of 2 over 0.15 times 0.20 to the power of 3 is equal to 0.0025 over 0.0012 or 2.08. Since Q is less than K, the reaction proceeds forward to reach equilibrium. Key takeaways. Number 1. Concentration changes shift equilibrium but do not change K. Number 2. Temperature changes shift equilibrium and alter K depends on delta H. Number 3. QC uses concentrations, KP uses partial pressures for gaseous systems. Number 4. Reaction quotient Q helps predict the direction a reaction will proceed to reach equilibrium.